Okay, that's nice homework. I think I'm just going to go ahead and go through all of them. Number 35. Number 35 says a laser in an audio compact disc player uses light with a wavelength of 7.8 times 10 to the second nanometers. We want to calculate the frequency of this light. Well, we know that. What's new? Well, new is C over lambda, of course. So that's what we're looking for. We're looking for frequency right there. Well, let's see what we're given in the problem. Well, C we know. C is going to be 2.998. 2.998 this is my given. 2.998 times 10 to the 8th meters per second. And I am given wavelength of 7.80 times 10 to the second nanometers. Now, yesterday I said that we can't leave it in nanometers. We've got to change it to meters because I got meters up here. My speed is in meters per second. So what I'm going to do is I'm going to take and I'm going to change that to meters. So for 1 meter, there is 1 times 10 to the 9th nanometers. My nanometers cancel. So I get a wavelength of, let's see here, 7.80 times 10 to the minus 7th meters. I believe that's correct. Let me get a calculator out here. Let's go with turning that on, and we've got 7.80 second EE 2 divided by 1 second EE 9. Enter. Yeah, I was right. Okay. All I do is plug and chug at this point. That means that my frequency is going to be equal to C, which is 2.998 times 10 to the 8th meters per second divided by 7.80 times 10 to the negative 7th meters. My meters cancel. Seconds goes to the bottom. So again, let me go ahead and there we go. Shrink up that calculator a little bit. Drag it over there. It's on my way here, and I got 2.998 times 10 to the 8th divided by 7.80. Oops. 7.80 times 10 to the negative 7th equals, I get a wavelength of 3 point, let's see here, sig figs, I need 3 sig figs, so it's looking at 3.84 times 10 to the 14th. So that's 3.84 times 10 to the 14th seconds to the negative 1, or seconds on the bottom, because that's where that went to. All right, let's take a look at the next one. 36. We've got an FM station that broadcasts at 99.5 megahertz. I want to calculate the wavelength of the corresponding radio waves. So again, what's new? Well, new is C over lambda, of course. In this case, I'm looking for wavelength. I'm looking for lambda. I know C is equal to 2.998 times 10 to the 8th meters per second. And we're given a frequency of 99.5 megahertz. Well, we said a megahertz is a million hertz, so this would be 99.5 times 1 million. which would be 99.5. You know what? Let's do this. 9.95 times 10 to the 7th, I believe, hertz, or per second. Cycles is understood. I could put cycles there if I wanted to. Seconds is basically, the bottom line is seconds is on the bottom. So I'm going to double check that just for fun. 99.5 times 1 million. Oh, I got an extra 0 there, don't I? Nope, I needed that 0. Alright, enter. 1, 2, 3, 4, 5, 6, 7. Yeah, I'm right. Okay, cool. So I'm ready to go ahead and plug and chug here. New 9.95 times 10 to the 7th over seconds is equal to 2.998 times 10 to the 8th meters over seconds, all over lambda. So I'm basically going to multiply both sides by lambda. Lambdas cancel out over on that side. And I wind up with a lambda on this side. And then I'm going to divide both sides by a 9.95 times 10 to the 7th. Cancels out on this side, and I wind up with lambda is equal to 2.998 times 10 to the 8th meters per second divided by 9.95 times 10 to the 7th over seconds. These guys cancel out. I'm left with meters, which is what I should, because that's what wavelength would be in. Let me grab my calculator again. And I've got 2.998 times 10 to the 8th divided by 9.95 times 10 to the 7th is about 3 meters. 3 sig figs would be 3.01, 3.01 meters. All right, next one. 36, that was number 36. Number 37. Number 37 says microwave radiation has a wavelength of about a centimeter. I want to calculate the frequency and the energy of a single photon of this radiation. Calculate the energy of Avogadro's number of photons. Avogadro's number is 1 mole. So here's what we want to do. We want to figure out the frequency and energy of a single photon. Well, let's start with frequency. So again, frequency nu is equal to c over lambda. So c, let's just go ahead and jump right to it. I know c is 2.998 times 10 to the 8th meters per second divided by the wavelength, but wavelength's got to be in meters, and we've got it in centimeters. So we're looking at 1 centimeter. Let's make that the right number, sig figs. 1.0 centimeters times 100 centimeters in 1 meter. So we're looking at 0.01, or with sig figs it's going to be 1.0 times 10 to the minus 2 meters. So So 1.0 times 10 to the negative 2 meters. These guys cancel out, seconds wind up on the bottom, and we get 2.998 times 10 to the 8th divided by 1.0 times 10 to the negative second is going to be equal to 2.998, which it would actually be with sig figs, it's going to be 3.0. 3.0 times 10 to the 10th hertz, or over seconds, cycles per second, which is equal to 3.0 times 10 to the 10th hertz. So that's the frequency. The other thing we want to know is the energy of one photon. So energy, we know that E is equal to h nu. If I remember right, I believe this is per photon. So what we would do is take and multiply our frequency that we just figured out. This is nu. And we'd multiply that by h. Remember, h is Planck's constant, which is 6.626. Times 10 to the negative 34th joule seconds. So all I would do is take this and go 6.626 times 10 to the minus 34th joule seconds times 3.0 times 10 to the 10th hertz, which is over seconds, or seconds to the minus 1, which means it would be in the denominator. These guys are going to cancel. I'm left with joules, and that is exactly, well, let's go ahead and do this. Drag this over here. It's going to be 6.626 times 10 to the minus 34th times 3.0 times 10 to the 10th, which is going to be 1.98 or 2.0 according to sig figs. 2.0 times 10 to the negative 24th joules. Double check that. I think I copied it right. Times 10 to the 23rd. Whoops. Times 10 to the 23rd joules. Now we want to know how much that is for an Avogadro's number of photons. Well, Avogadro's number is, we're familiar with that. That is 1 mole is Avogadro's number. So what we're going to do is we're going to multiply this 2.0 times 10 to the negative 23rd joules times 1 mole, because this is really joules per photon. Each photon has that much energy, so we're going to multiply that by 6.02 times 10 to the 23rd photons, 1 mole of photons. Photons cancel, and that's going to be equal to, let's go ahead and multiply that out. We got 2.0 times 10 to the negative 23rd times 6.02 times 10 to the 23rd. It's going to be about 1, and that's about 12. All right, so that would be 12 with 2 sig figs. 12 joules. All right, last but not least, 38. 38 says primary visible emissions of mercury occurs at 407 nanometers excuse me, 404.7 nanometers and 435.8 nanometers. We want to calculate the frequencies of these emissions, then we want to calculate the energy of a single photon, and then we want to calculate the energy of a mole of photons. Well, mole of photons, again, 6.02 times 10 to the 23rd. So let's go ahead and get our frequencies first. Let's go ahead and do it for these two wavelengths. I know that nu is equal to c over lambda. Again, these are in nanometers. Yep, nanometers, so I'm going to have to convert these. So let's go with 404.7 nanometers times in 1 meter. There is 1 times 10 to the 9th nanometers. Nanometers are going to cancel. So I get 404.7 times 10 to the minus 9th meters. So that's my wavelength. So if I want to figure out the frequency, I'm going to go ahead and take nu is going to be equal to 2.998 times 10 to the 8th meters per second over 404.7 times 10 to the minus 9th meters. And that leaves me with, let's see here, 2.998 times 10 to the 8th divided by 404.7 times 10 to the minus 9th is going to be equal to, oops, I didn't get a good look at that. I need 4 sig figs, so I'm looking at 7.408 times 10 to the 14th. So 7.408 times 10 to the 14th hertz, which is the same as cycles per seconds, or seconds to the minus 1. And I think I'm going to write it that way. Seconds to the minus 1. That just means it belongs in the denominator, so it would be over seconds. All right, so there is my frequency, and I need to figure out the energy of a single photon. So again, we're going back to E is equal to h nu. We just figured out nu, so the energy is going to be equal to 6.626 times 10 to the minus 34th joule seconds times nu, which we got as 7.408 times 10 to the, oops, I think that was 14th, times 10 to the 14th over seconds, because seconds to the minus 1 belongs down there. My seconds cancel out, and I get, I'm going to take my answer. It's going to be second answer times 6.626 times 10 to the negative 34th, and that's going to be 4.908 or 4.909 times 10 to the minus 19th. 4.909 times 10 to the minus, what was that? 19th joules. So that is the energy for one photon. For a mole of photons, I would simply multiply that by 6.02 times 10 to the 23rd. So I would take 4.909 times 10 to the negative 19th joules. That's per photon, times, there are 6.02 times 10 to the 23rd photons in 1 mole. So my photons cancel. So per mole, it would be, and I'm just going to take my answer, so the second answer times 6.02 times 10 to the 23rd. It's going to be, well, this should be 6.022, so really I still need 4 sig figs. I'm going to go with 4 sig figs. If you went with 3 sig figs, it's not a big deal. We're looking at 20, oh wow, 295,000, we'll go 295,500. 295,500 joules. For the other part of the problem, you would just put in 535.8 up here, 535.8, and just do everything exactly the same. You would go through the same set of calculations. You would take your answer and use it in the next part of the problem. You would just repeat everything with 535.8 nanometers. So I'm not going to do all that over.